this interference picture shows us that there are waves. We don't observe them when we watch photons, but we must conclude that they somehow exist. And as every wave, they have parameters like amplitude, relative phase, direction of propagation, frequency, etc. And we remember that the intensity of the wave, which we observe as number of photons at some particular unit area. And if we send only one photon in this experiment, this intensity graph has a physical meaning of the probability of catching the photon at some particular area on the screen. We just have to divide it by the total number of photons in the previous experiment. And we obtain the share of photons which arrive at each position. This share can be considered as the probability for one particular photon to arrive and be detected in this area. And since it is proportional to the intensity of our mysterious unseen wave, which is itself proportional to the square of the wave amplitude, we can conclude that the probability of the photon detection in some area of the space is proportional to the squared amplitude of some undetectable wave attached to it. This mysterious wave has a name. Physicists call it the wave function, and its amplitude at each point is called the probability amplitude at this point, because it is connected to the probability of a particle detection there. Now we are convinced that this wave function exists somehow, though we can't directly observe it. Where does it exist? Well, you already know that one possible way to look at this is to employ the notion of the multiverse, which we slightly discussed on the previous week. The photon itself acts as a particle, but in the bigger picture of the world, in the multiverse, which contains many copies of identical universes, it has the structure of a wave. Now, I don't expect you to perfectly imagine or even understand it. Richard Feynman once said, "Nobody understands quantum mechanics," and he had reasons for that. Now, even more astonishing result. What if we repeat this experiment with electrons? I mean, with light there were always controversies about its nature, but electrons, we are used to imagine them as small balls, right? No one imagines a photon as a small ball. I don't think there is a correct way to imagine a photon, but electron. It even has a radius, just like a ball. It is definitely a particle, a bullet, so it must act like a bullet. Well, apparently it does not. It is much more difficult to show, but electrons have interference in this experimental set too, which means they also have a wave function and the probability amplitudes. And they are also waves in the multiverse picture. But these waves have much larger frequencies and much sharper distributions over the space than that of photons. It appears that everything in the universe has a wave function and shows the wave-like behavior. However, the more massive particles have sharper peaks in their probabilities distributions, which allows us to detect them in certain positions with higher probabilities. This wave-like nature of everything was first proposed by the French physicist Louis de Broglie in 1924, and is known as de Broglie relations. And it appears that describing any particle in the terms of its wave function is much more rigorous and informative way of description than just specifying its classical parameters like position and momentum. So let's talk about wave functions.